and then vibration isolation. I think I sent you some notes, didn't I? I don't know whether you've had a chance to look at them, but we'll go through that. But initially, I just want to, I'll share my screen. I think I might have sent you this as well, but this, you've got access to the Fantech catalogue, haven't you?
Yep.
It's in our files, and this section, general acoustic information, is very useful to have an understanding of sound power level, sound pressure level, insertion losses, which is attenuation of sound, airway velocities. So I don't want to go through all this now because we could spend quite a bit of time just talking about this, but if you just want to get a bit of background, this is quite good. And it gives noise ratings, dBA levels for different things that we encounter. So jet aircraft at the top there is 140 dBA. That's very noisy if you're standing beside a jet aircraft. But then, you know, you go right down to very low noise levels. Generally, for office areas, say 40 dBA, quiet bedroom might be 30 dBA. So it's good to get a feel for those numbers and what you're trying to achieve. And I think I might have mentioned to you that there is an Australian standard, AS2107, which is in our files, which has recommendations for sound levels. Then it's got noise rating curves, NR curves, NC curves. The NR curves are used more often now, and so on. So, and what's this one talking about? Spectrum corrections for airway velocity. So if you're doing manual calculations, these are some corrections. And some attenuation you can achieve with line duct, internally line duct, 25 millimetre, 50 millimetre, and bends as well, square bends with turning vanes, square line bend, with and without turning vanes. So that's all useful information and worth just being familiar with anyway. And it's a good basis to understand acoustics. Now, if you're doing acoustic calculations, this is the product selection program from Fantech. You've got access to this as well in the file. So if you have to do any acoustic calculations, and sooner or later you will, this is quite useful. So you can put in here the sound power level of the fan. When you've done a fan selection, you'll get the sound power level, so put that in. Duct system effects brings up this screen where you can put in the length of duct, any square bends, whether they're lined or not. So you've got all these options. You can choose. Sorry, we're getting a bit of feedback. Can you hear me okay? I'm getting feedback on my end. Circular, rectangular duct, you can put in the sizes, and then you can choose whether it's unlined, 25 internal, 50 internal, and we'll put some numbers in there for you, and so on. So this is very useful if you're required to do a calculation. And just work your way through. Direct sound to terminal. You know, is it 100% of the sound power or is it 50%? You have to make a few judgments on these things, but generally it's pretty self-explanatory. And it puts these factors in. And when you get down to the bottom, it'll tell you how much attenuation you need, and then you can select a silencer from the catalogue. So if you click on select a silencer, you can go here and actually select a silencer. But what I want to talk to you today about is a manual way of doing that. If you want to do a quick assessment of an attenuator, so you're not not waiting on a selection from a supplier such as Fantech. When they do a selection, they'll give you all the data you need, including the pressure drop and so on. But you can do it yourself. So I'll just go to these notes. So in the notes, I'm giving you a few tips to assist in selecting attenuators, particularly rectangular type. So I'm going to focus on those. We generally aim for a maximum face velocity. So that's the duct velocity where it's connecting to the attenuator of about 5 to 6 meters per second, because the attenuator has splitters in it and the velocity will increase as it goes through. Obviously, the velocity depends on the free area of the attenuator selected. So, for example, an attenuator with 33% free area and face velocity of 5, the airway or the passage velocity would be 5 divided by 0.33 or 15.2 meters a second. So it's quite high. So what tends to happen is as the velocity through the attenuator increases, the noise regeneration increases. So the attenuator actually starts to regenerate noise. So you need to be careful of that. Generally, we go up to about 15 meters per second passage velocity as a maximum recommended. So that's one of the things to consider. Another one is the higher the airway velocity, the higher the pressure drop. The NCC stipulates 40 pascals maximum for attenuators. We used to work on about 50, but the NCC now says 40. So we have to comply with that. So I'll just show you. This is a part of the NCC, section J, what is it? J6D5 fans and duct systems. And I've highlighted this here. 4G, attenuators must not exceed a pressure drop of 40 pascals. So when you use fan static calculations, that's all you can't allow more than that. And you can't select for more than that. Okay, let's go back here. So for an air handling unit, this is just a bit of information so you know what to expect. If attenuators are required, normally the return air attenuator will require a higher level of attenuation or sound absorption than the supply air attenuator. Now, this is quite common. If you've got attenuators on both sides, the return air will normally be a bigger attenuator. And this is because on the supply air side, there are normally several or many air outlets, and the sound power is distributed to all these outlets. So it doesn't just go to one, it goes through the whole system. But on the return side, there might be only one outlet or inlet, return air grill, which is quite common. So you might have several supply air grills, but only one return air. So on the inlet side, all of the sound power on the inlet side goes to one grill, or however many return air grills there are. So you need more you quite often need more attenuation on the return air side than on the supply air side. And the return air attenuator is likely to be longer than the supply air. I'm just mentioning all this because this is good information to understand what to expect. Now I've got a selection exercise here. The application, it's an air handling unit serving a critical medical area. Supply airflow 3,500 litres per second, return airflow 1,750 litres a second. So basically what I'm saying here, with those sort of airflows and being a critical medical area, it's probably an operating theatre. So I'm just making this up, okay? But that would be typical for an operating theatre. Now, do you know what the requirements are for attenuators that serve an operating theatre or a clinical space where patients are being looked after in a hospital or any medical centre? There are Australian standards and state-by-state requirements for lining of ductwork or attenuators. Are you familiar with that? Oh, Simon, I can't hear you.
Yep, sorry, I only mute.
Oh, yeah, okay.
Yep. Basically, in Australia, I think for the attenuator, they don't want to use like the more fibers because there's like particles. So I don't know what material do you want on the con. Because
So
basically, if it's a for evaporating theater, those particles will be
yes,
affected to the joint.
no, that's right. And so what we what we usually do here is put a lining on the. Sorry, I'm getting feedback again. Is that people in your office talking? Yeah. Okay. Well, if you want to mute your microphone, that's okay, and just put it on when you want to speak to me. So what we use in Australia is a Melanex or a mylar lining on inside the attenuator, which stops the fibres coming out into the airstream. And the Fantech attenuators are called Q-seal when they have this lining on the attenuation material. So that's the first thing we have to solve, that it's a critical medical area. We're going to have to use the Q-seal type attenuator. Okay, and I've just written down here some fictitious numbers that I've come up with. Supply air attenuation requirements at those frequencies and return air attenuation required. And so I've said, using the Fantech information, select suitable rectangular attenuators to satisfy these requirements. Bear in mind the application, which we've just talked about, and NCC requirements, which is the 40 pascals pressure drop. So now we'll have a look at this is some more information out of the Fantech catalogue. So it's rectangular duct attenuators. There's a few types. There's the RS series, which has straight splitters, RT, which has tapered splitters, and then there's RTQS, which is tapered splitters with the Q-seal membrane, which is suitable for our application of a medical centre. So then it's got all this data. You can have a look through this. That's the RS straight splitter, RT tapered splitter, and then we get down to the RT Q-seal series, which is what we're looking at. So I've done a bit of exercise myself, but I'm just thinking this would be a good exercise for us to work through, rather than just give it to you to work on. I know you're busy, so we can work through it. So if you look at that data that I gave you, on the supply air side, I've come up with three possible selections. One is an 07 C2. The next one is a 10 C2, which is down here, this one. And another one is the 12E. So when we go up in number, sorry, when we go up in the letter after that number, it's increasing the length, right? The number itself refers to the free area over here. So the lower free area obviously is, it's going to accelerate the air more. As you increase the free area, the airflow doesn't accelerate as much. Generally, we select attenuators probably from 27 to 38%. But, it just depends. So I think I've said to you before that in our previous session that the critical frequencies are usually 125 and 250. So what you tend to find is when you're selecting an attenuator, you're going to be concentrating on oh, sorry, I can't highlight that very well. 63 is not so critical, but 125 and 250, we need to achieve those. And then above that frequency, normally they just fall into place because you get a lot more attenuation at the higher frequencies, which is because of the wavelength of the sound. At low frequencies, it's got a long wavelength, so it's harder to attenuate. So to achieve those numbers, an O7C2 will do it. We're getting, so we wanted 6 at 63, 11 at 125, and 19 at 250. So we're going to achieve it there. With the 10C2, we're getting 6 and 11, which is what we wanted. And with the 12E, we'll get 6 and 12. And then the rest are fine. So that's 3 options. Varying lengths, and as an attenuator gets longer and bigger, it's going to cost more. Okay, so really what we're aiming for is to get the smallest attenuator we can, but still achieve obviously the attenuation, but also the pressure drop. So let's just have a look down here. So there's some graphs where we can calculate, we can work out the size of the attenuator, but firstly, so if we're looking at the O7C2, so we go to C2, okay, this one here, and I've just marked on here where the 40 pascals is. If you make that your maximum, you go across to the O7 line and you get a face velocity of about 3. Okay. If we go to the 10C2, so we're still in the same chart, go across to 10, we get a face velocity of 4. So this is the duct velocity at the inlet to the attenuator. If you go to the 12E, so you go down to this one and go across 40 pascals to 12, it's about 5 face velocity. So there's a few things at play here. Do you want to have a low duct velocity or a higher duct velocity? Because the higher you make the duct velocity, the smaller the duct is going to be. So you're looking at the duct size, you're looking at the attenuator size, and you're trying to get a maximum of around 5 meters per second face velocity. So once we've got the face velocity, and we know what the airflow is, we can calculate the cross-sectional area of the duct, okay? And from that, we can go back to these module widths. So each of these different styles of attenuators has set module widths. Now, I'm only talking about Fantech here because that's the one we use the most in Australia, but there are others who manufacture attenuators, so you need to look at these things depending on who you're dealing with. But if we're looking at Fantech, you've got these standard module widths. So if you've got a duct that's it's basically going to try and match up with the well, the height could be important if it's in a ceiling. The height will be important, but if it's in a plant room, the height and the width can vary depending on how much space you've got. So from whichever one you choose, let's say you choose the O7C2, you've got these module widths. And if your duct is around, say, 1 metre wide, you might select 1100 for a width. And then from that, you know the area, you can calculate the height. So I've said here, the steps in the process: select the suitable attenuator from the tables, which includes the length. Read the face velocity from the graphs based on a maximum of 40 pascals. Calculate the face area, so that's the airflow divided by the face velocity. And then select the standard width that suits the duct width, and then calculate the height. And the height has got to obviously fit the space that you've got available. So is that straightforward? And I did the same exercise for the return air attenuator. You can just work through that. I mean, if you want to do an exercise, have a go at the return air one. And
Yep.
I'll tell you what I've come up with on the return here. I had 07E, 10E. Now this is an interesting one, 12F or 12G. So if we have a look at, just have a look at that. So we're looking for attenuation of from 63 to 250, we're looking for 6, 14, 22. So if you look at the 12F, 12E, you've got 6, 12, 22. So, sorry, that's not it. 12F, 7, 13, 26. Hang on, I'll just get rid of that. So I said 12F or 12G. 12F has got 7 at 63, which is okay, but it's only got 13 at 125. We wanted 14. But above that, everything else is fine. So we're 1 dB low at 125. You could look at that and say, is that really going to be a problem? In most cases, it won't be. It's probably not that critical. Or you can go to a 12G and satisfy all those requirements. So there's a bit of, toing and froing, trying to decide which one is the best one. And look, to be honest, this is not the way that we normally do it, but if you have to do it, this is a method you can use. The way it normally happens is in the contracting environment, once we've worked out the attenuation, you'd send it to someone like Fantech and ask them for selections, and they'll come back and give you the most economical selection for the airflow, for the pressure drop, for the attenuation required. But that could take some time. And if you need to do something in a hurry, you've got this method. And this is, to actually do this a couple of times gives you a better feel for how it all works. Okay. So what else have I got there that I can show you? Also in the Fantech catalogue, there's these do's and don'ts. These are worth looking at because it's important to install attenuators with good airflow in and out. If you install an attenuator with an abrupt entry, you will affect the performance. If you install one straight after a bend, it will affect the performance. So you've just got to realise that you want good straight airflow coming into an attenuator so that you can fill all the passages of the attenuator and get the best performance. So a few examples here. Don't have a sharp inlet. Have a nice long inlet to the attenuator, and you want to align the direction of the splitters so that the air can fill up the attenuator. In this top one here, if you had the splitters going horizontally, then it's not going to work very well because the air is going to tend to want to go through one passage only and not fill up the attenuator. So just imagine you're in the airstream. How are you going to fill the attenuator to get the best performance and lowest pressure drop? The next one, they've got a damper right before the attenuator. Well, you wouldn't do that. You're creating turbulence at the inlet. You put your volume damper back upstream and have a nice entry to the attenuator. Don't put it right on a bend, as I said. Again, the air's, if it's coming around the bend, it doesn't know which splitter it's going to go to. You want to straighten the air out and turn the splitters over in this case. See how they've done that? They had vertical splitters. Now they've made them horizontal so that as the air comes around, it can fill the attenuator. From a fluid flow point of view, that makes more sense and it works better. In relation to axial fans, again, a nice long inlet. Don't put a sharp inlet at the inlet, a sharp transition at the inlet. Have a good long straight one or gently sloping, and the same on the outlet. If you've got a cylindrical silencer with a pod, sometimes we put a pod in the circular attenuators to get higher performance, but that means higher pressure drop and disturbs the airflow coming in. So in the first, where it says you don't put this podded attenuator right up against the fan, because that's going to stuff up the fan's performance. But if you move it back by at least 1 fan diameter, the air will straighten out and the fan and attenuator will work okay. Same thing here, centrifugal fan. Don't put it on the outlet of the centrifugal fan, because the air is coming up to the top, and it's not going to go evenly through the attenuator. So put in a spacer duct to let the air straighten out, and fill the duct before it goes into the attenuator. And a few other examples there. So you can have a look at those yourself anyway, and get some more information. What else did I? Sorry. So I think that's probably all I wanted to talk about with attenuators. While I've got you here, have you got time to have a chat about vibration isolation?
Yeah. Yes.
Okay, so we'll go to that.
Are you still hearing feedbacks? No.
I think it's only when there's people talking near you.
Ah.
So at the moment it's quiet.
Yeah.
So I'll let you know if I'm getting noise coming through. So vibration isolation. I can hear background noise now. So vibration isolation. Now you probably have had a fair bit of experience with vibration isolation, I presume. So yeah, what I'm going to say is probably not new information for you, but if you've got any questions, just let me know as we go through. So you can see these notes up there, can you? Vibration isolators play a crucial role in HVAC systems by reducing the transmission of vibration between the mechanical equipment into the building structure via the equipment support system. So the vibration isolators act as a barrier to transmission of vibration. And this is important for several reasons. Firstly, the equipment life. Properly selected vibration isolators prolong the life of the HVAC equipment. Vibration will lead to wear and tear over time. Noise reduction. Now, this is probably the biggest thing that we find. Vibrations are transmitted from the HVAC equipment into the equipment supports and building structure, causing undesirable noise. Now, this can be very difficult to find. If you've got something that's vibrating and it's not isolated properly, it might be a pump, might be a pipe, a duct, or a fan. It's very difficult to find where it's coming from, and it comes into the building as noise. So if there's vibration in the structure, it'll come into the space as noise. So the occupants of the building are likely to experience discomfort due to the persistent noise transmission through the building structure. And there are building regulations which stipulate what the acceptable sound levels are. So we have to comply with that. So vibration isolation is normally achieved by supporting the equipment on resilient elements such as springs or rubber mounts, which compress under the equipment weight. The amount of vibration isolation is directly related to the amount of compression or static deflection of the anti-vibration mounting. So that's important. If you've got a spring, there are optimum levels of compression, and you have to make the selections, but you don't want to fully compress a spring because it doesn't provide any vibration isolation if you do that. And you need it to be aligned straight. You don't want it on an angle because that's not going to work very well either, particularly if it's a cage spring, because it's going to transmit vibration through that cage. So I've just listed down here some types of equipment that require mounts, and I'm sure that you're familiar with all this. Axial, inline, centrifugal, or mixed flow fans. We can use the fast clamps for small inline fans. Have you seen those? Yep.
Yep. Yep.
They provide, you can hang with those, but they also provide some vibration isolation. Rubber and shear or spring mounts. They can be hanger type or floor mounted. Sometimes we have to use seismic mounts so that if there's an earthquake, the equipment is held in place and doesn't fall off its mounts. Centrifugal fans, usually floor-mounted springs, may require seismic mounts if it's in an earthquake-prone area or a building that requires seismic mounts. I've got a picture of a centrifugal fan that I can show you. I'll make it a bit bigger. So there's a centrifugal fan. These would be seismic mounts, so that they're springs, but they're retained as well. So if there's movement, if the building is shaking, the fan doesn't fall off the mounts. We had an earthquake in Australia, 1989, I think it was, around Newcastle area, and a hospital was badly affected because it didn't have any vibration, any seismic mounts at all. And a lot of the major equipment actually fell off its mounts and didn't keep operating. So that was a major problem because it was a hospital that should have that was going to have a lot of patients in an earthquake situation, and the HVAC equipment was not functioning because it had fallen off its mounts. So seismic mounts are important, particularly in those sort of environments.
Just a question,
Yep.
Peter, on the seismic, that spring mounted. Just basically, because if there's a equipment, then the like a ductwork cage should like a vertical discharge. So do we need to know already the height of the seismic because it may affect the length of the duct length for manufacturer? Because it basically, if we don't allow it correctly, those lengths like length that have been ordered will be probably there will be changes on that one.
So what was the situation again? You got a discharge
So
duct.
yep, if we have like equipment HU like a vertical discharge ductwork, so basically
Yeah,
there's an HU and a vertical with this spring.
yeah.
So do we need to know already the spring height so that we could assume the length? Because basically it will affect length if we don't assume correctly those spring mounted.
Yeah, no, that's a good point. Yeah.
Yep.
If you're talking about an air handling unit,
Yep.
it's not common for an air handling unit to be mounted on springs.
Yep.
Uh, they usually just sit on a bit of rubber pad because the fans inside the air handling unit have springs already. So you don't normally need them if that's the situation. So is that what you're talking about? Like an
Yep.
air handling unit? Yeah. It's
Yep.
very rare to mount an air handling unit on springs.
But the
Uh,
rubber pad, do we have like a typical height or thickness of that
well,
one? Or
normally if you've got a concrete plinth, an air handling unit would probably be mounted on waffle pad, which is about say 15 millimeters thick. So you could allow 15 for that.
yes, too
Um,
minor.
but the springs for the fan, which is inside the air handling unit, that will be on springs inside the air handling unit. So you don't need to worry about that. And you don't need where the fan is vibration isolated inside the air handling unit. You don't need a flexible connection for the ductwork. You can solidly mount the ductwork to the fan to the air handling unit.
So
That's the way.
basically, this will just affect those inline or probably axial fans. Because basically, it will just lift uh, a bit because there's a spring mounted. Because axial fans have
Uh, No, it won't change the level of the fan. Is that what you're saying? That you're lifting the fan? No, it'll just, well, it's got to be supported. So it's supported on springs, which are set for the weight of the fan, selected and set for the weight of the fan. So it's not something that you really have to be concerned with. All I'm trying to point out to you is that to be aware that that should be shown on the drawings, that there will be either spring hangers or rubber hangers or whatever it is. If it's not a floor mounted fan, it might be springs or it might be rubber again. Just need to show that they're there. They need to be selected, well, the engineer in conjunction with the fan supplier needs to select the correct springs. But I wouldn't be concerned about the levels of duct or fans or anything like that, because that won't change. It's just a matter of selecting the springs correctly. Does that answer your question?
Yep.
Okay. So plug fans, are you familiar with plug fans? Yep. Again, they use them a lot in air handling units now, the bigger ones. So we used to use centrifugal fans, but now we tend to use plug fans. So they can be either floor mounted on springs, or they might be in an array on the wall of an air handling unit. I don't know whether you've seen that. I might have a picture of that, I think. Yeah, this one. Have you seen this sort of thing? So these are
Not
all
yet.
these are plug fans. They're plug fans in the boxes, and they can make this a wall of an air handling unit. So you can have any number of plug fans making up the wall of an air handling unit. And the reason they call them plug fans is you can plug and play. If one fan fails, you can pull it out and replace it with another one. And you can have one fan running, or you can have multiple fans running. So these two arrays are 12 fans. So if one fan fails, you can take it out and put another one in. But if you want to have variable volume, you can either change the speed of all the fans, or you can turn one off and let the rest run, or turn half a dozen off and let the rest run. So there's lots of flexibility with that type of system. So that's something that's coming in, or was coming in a bit, in recent years. And a plug fan inside is another one. This is just a plug fan that you would put inside an air handling unit. It's an open setup, so you've got to put this inside a sealed chamber. So the air inlet here that has to be up against the wall. Excuse me. So you'd have a flexible connection between this flange and the wall of the air handling unit for the inlet, and then the outlet side is just a sealed box. And then you can have your discharge wherever you want it. You can come out the top, because there's no ductwork between there and the discharge. There's an opening in the air handling unit. You can go out the top or out the side, and that's got some advantages. If you're in a space where you haven't got the room to go up, but you can come out sideways, that's ideal for that, because you don't have to have a direct connection between the fan and the supply air duct. And this obviously, the frame would be mounted on springs inside the air handling unit. So that's all flexibly isolated and a flexible connection on the inlet. So that's why I say you don't have to put the air handling unit on springs. They probably just sit on rubber, because if there's any residual vibration, the rubber would take that out. Now pumps are normally floor mounted on springs, springs under outriggers. They may have an inertia base with springs. You're familiar with inertia bases? Got a picture of that, I think. So here's So here's the pump sitting on a concrete base. That's an inertia base. And what that does is when the pump starts, it's got a lot of inertia. And this inertia base is a solid concrete block. I think it weighs about 1.5 times the weight of the pump. And you put that on springs. So these springs have to be selected for the combined weight of the block, the concrete block, and the pump, and in this case, some of the pipe work.
So that concrete block is like has a space between those two concrete pads, the bottom.
It's about 20 mil, probably.
Yep, like a 20
Yeah.
mil, just so that it will just like.
Yeah, so it doesn't touch. Yeah.
Mm.
But usually it's not much. It's probably about 20 mil, 25 mil. And those springs, as I said, have to be selected to carry all that weight. But when you select a pump, if you're putting an inertia base in, that would the frame of the base would be normally supplied by the pump suppliers, because they would calculate the weight that you need, but they wouldn't do the concrete. So you'd have to do that on site. So you put the base down, fill it up with concrete, and then set the pump up. If you don't have an inertia base, then the pump is mounted on springs on the floor. But you'd normally use an inertia base if you've got a multi-story building and the pumps are up high in the building. Okay, because the building, I don't know how to explain this very well, but the higher you go in a building, the more the vibration will pass through the building. If the pump is in the basement of the building, then you may not need an inertia base at all, because you're down in the earth, solid ground. So that's just one rule of thumb to keep in mind. Where do you need an inertia base? If you're up the top of the building, you probably need one. If you're down the bottom, you probably don't. So just bear that in mind. Air handling units, as I said, internal centrifugal fans or plug fans, which come with springs, or internal wall or plate mounted plug fans. Fan coil units would have internal centrifugal fans with rubber mounts, not usually on springs, but they're on rubber mounts because they're only small usually, or small plug fans with rubber mounts. Fan coil unit cabinet is sometimes mounted on springs because the vibration isolation of the fans inside the fan coil units is probably not as good as it is for an air handling unit because they're mounted on rubber. So you might need to mount a fan coil unit on springs or on rubber and shear. So it just depends on the type of project, whether that's an issue, and and where the fan coil unit is located. If it's located directly above a space, you might need some vibration isolation for the cabinet. If it's out in a plant area or a storeroom, you probably don't need it. You might just put a rubber mount there to absorb some vibration, but you wouldn't need much. Chillers are normally mounted on waffle pads. They can be on springs. Again, depending on the acoustic requirements of the project, it's not that common to put them on springs, but you might need seismic mounts, or not necessarily seismic mounts, possibly seismic restraint, which means, let's say a chiller is mounted on a waffle pad, so it's sitting on a rubber pad on the concrete floor, but you put some steel restraints there so that it can't move. But I've got a picture of a chiller. So this is a water-cooled chiller. This has actually got seismic springs. That's not common, but sometimes you have that. So that's what they look like. So they've got the springs. It can't come off the springs. In other words, if those springs are open and they haven't got restraints there, and there is an earthquake, the chiller might rock around and actually fall off the mounts, and that's going to break the pipes you know, it's not going to work. You're going to have a flood in the plant room and the chiller's not working. So just things to bear in mind. Cooling towers, very rarely are they put on springs or anti-vibration mounts, but they probably would sit on waffle pads again. So you've got a 15mm pad that it sits on, 10 to 15 rubber, just to take out a little bit of vibration that may occur. And sometimes you need seismic restraints. The same with boilers. Condensing units usually sit on rubber mounts, rubber and shear, which are quite often supplied by the manufacturers. They just give you the mounts that are recommended for those units. Package units usually sit on waffle pads, very rarely on springs or rubber and perhaps small rubber and shear mounts. The fans and compressors are normally isolated internally as well. And sometimes you might need spring hangers for pipe work. In some specifications, they ask for spring mounts on the pipework for a certain distance away from the pump. So that might be another application. So what else can I show you? There's a cooling tower here. It's a little bit hard to see, but so you can see the frame of the cooling tower there, and it's sitting on a concrete beam. So in this case, there may or may not be a rubber pad there. Usually you'd put a rubber pad between the frame and the concrete just to give it some separation. If there's any vibration from the fans up the top there, which there may be, the rubber pad will be sufficient to isolate that. Now, this is out of the Fantech catalogue again. There's a bit of information on vibration isolation and the importance of it, things that I've just been talking about. And it gives you some technical information about this, how they're selected and their isolation efficiency for the different types. So that's something you can have a look at if you want to read some more about it. And what else have we got? Also in the Fantech catalogue, there's some do's and don'ts on vibration isolation. So this is pretty handy information and worth being familiar with. So what this is saying is don't bolt the fan directly to the building structure. Obviously, you never do that. So you're going to sit it on, put some feet on and put some springs there, or rubber and shear. This is a roof-mounted fan. This is an interesting one. Instead of bolting it straight onto a concrete opening, put some foam or rubber padding in there between them, because there will be some vibration in the housing of the fan. So if you put that, what they're suggesting is some foam tape on the opening there, so the fan can sit on that, and that will provide sufficient isolation of the vibration. Now this one's showing that the spring is fully compressed. So this is just the spring selection. It's got to be selected for the weight that it's got to carry. Okay, so they're saying that's bad. You don't want that, because all that's doing is allowing the vibration to go straight through that spring isolator into the structure. You need to have it expanded to the right level to get the vibration isolation. And this one is, if you've misaligned the hanging point, so it's got to be lined up correctly so that the spring, if it's in a cage, is not touching the cage. So it's all obvious things, but just a few tips. All right. Any questions?
No, probably the question is, how will I know if I need seismic mounts or spring? When do I need do I need to make it a seismic mounted or a spring only?
Well, normally it does depend on the size of the fan. Normally for axial fans, we'd probably have rubber mounts. When you're selecting fans, the manufacturers will usually recommend the types of isolation you need. But if you're drawing it, then you need to know, I suppose. Well, all you need to do is make a note that you've got vibration isolation. When the fans are selected, the fan manufacturers will usually recommend the types of mounts that you need. So if it's an axial fan, they might, say a small axial fan, they'll say, well, just rubber and shear is okay. If it's a big axial fan, they'll say springs and all the extra things you need with that, which are mounting feet and so on. For a centrifugal fan, they would normally offer springs because they're a big bulky fan with a lot more weight. And pumps, they'll normally offer springs. So you need to be aware that vibration isolation is required, and the manufacturers of the equipment will recommend what you should use. That's not to say that you can say, well, I don't want to use rubber and shear, I want to use springs. You can if you want to, but there's a cost involved there as well. It's generally not needed for small axial fans. If you've got a car park exhaust fan or a smoke exhaust fan that's mounted horizontally, you use springs for that because it's a bigger animal that you have to support. Probably, I probably haven't answered your question very well there, have I?
Yeah,
Was it?
because basically it's quite a judgment for you. Some of it will be your judgment if you want to use a
Yes.
seismic, but that's a good reference that we have discussed.
But
So probably,
with seismic, it's a code requirement for certain buildings. It's not very clear on what you need to do, but to give you an idea, there is an Australian standard that sets all this out. I think it's AS 1170, but don't quote me on that. It talks about the importance of a building. So importance levels, obviously, they're very high for a hospital, for instance, where there's lots of people who are not well and can't just jump out of bed and run out of the building if there's an earthquake. Okay, so they've got to be protected, and you've got to protect the equipment in the building, and you don't want. I mean, it's not just the HVAC equipment; it's the whole building. You know, you don't want bits falling off the building and injuring people, particularly people who can't escape. So there's the importance. There's the number of people. Another building would be, say, an auditorium where there's, or like a picture theatre or something, where there's a lot of people in one place and they can't get out of the building quickly. Those sorts of things determine the importance of the building. There's also the location of the building. Is it in an earthquake-prone area? You know, and some areas are not prone to earthquakes, but a lot are. I don't know about the Philippines. I mean, do you get earthquakes there? I suppose you do.
yep, mostly
You're probably in that, what do they call
ring
it?
of fire, ring
The
of
Ring of
fire.
Fire, yeah.
Yeah,
Because it comes down from the US down through
yeah,
the Pacific and
yeah,
down into New Zealand.
yeah.
It doesn't really touch Australia, but we have had earthquakes, but not really severe. But they can occur anywhere. So it does depend. So if it's a healthcare building, yes, you do need seismic. If it's, just a small building, residential buildings, well, you don't need it. So you need to be aware of those things. But you're always going to need potentially some form of vibration isolation, whether it has seismic or not. You still need vibration isolation because otherwise you're just creating noise problems in the building.
Yep.
Okay, anything else?
The is wait a moment.
Okay.
Probably I look after it again once I have time, so that probably I ask. Because this vibration in, because usually I just issue the fans. Then the contractor, like right now, I'm just completing the drawing so that they could issue it to the system. I don't
Yeah.
know, system contractor just said so that they could just probably do the computation or the required size meet. I don't know. This
Right.
we have one project now that he's tasting to finish the drawings fast so that he could go to the system equipment.
Yeah, okay. Oh, well, I don't think you need to worry about the detail of the vibration isolation, but be
Yep.
aware or note on the drawings where it is required.
Mm.
So generally for fans and pumps and all those things, you will indicate that the vibration isolation is required. If you've got seismic and you've got air handling units, you probably need seismic restraint, but
Mm.
not seismic springs as such.
Mm.
Chillers, if you've got chillers, they may need seismic springs if they need springs, but it really depends again, where is the chiller located in the building? If it's at the top of the building, you may need springs.
Yep.
If it's down the bottom, you
Yep.
won't. I doubt that
Yep.
you would. And it depends on the type of chiller. What type of refrigeration compressor does the chiller have? And nowadays they're usually centrifugal. If they're like the magnetic bearing type, they don't need any vibration isolation, and I've witnessed that myself. They're just amazing. They don't vibrate. So there are lots of variations, depending on the type of equipment and so on. But just have to do it on a case by case basis.
Yes.
Okay.
Yep. Also, I've encountered one just out of the topic. This
Sorry.
one. I have encountered one like engineering discussion previously. Let me
Yeah.
share with you. Like, so I've got garbage. Food. I don't know because I've just assumption and probably let me never see my screen. Have you seen it, Peter?
Sorry.
Have
Yeah.
you seen my screen? Yep. So basically, the probably consultant wants to put like a return air, like a which is to propose. So we will have like return air pot for the garbage chute.
Yeah.
Yep. So basically, the problem is how to determine the airflow, correct
Excuse me a
airflow.
second. Excuse me a
Yep.
second, Simon. Hey. Sorry, I'm pretty good.
Finish? I
No,
finished.
no, finish.
Oh, okay, all right, well, that's all right. Yeah, only big one. But, so we have two bedrooms, isn't it?
Sorry, Simon.
No worries. This will just be a quick. Just probably your opinion. So this is the problem. They want now to have a return air grid.
Yeah.
Yep. And we determined that each garbage chute has a fan which has like a 80 liters per second total capacity.
Yeah.
So what I assume is that it will only be at 80 liters because if this is 80 and 80, so total 160. But the garbage chute will not be open at the same time. So just assume like the minimum, the 80.
They're asking for a minimum of 80, are they?
Yep. Because basically, if we will assume 160, the grill will be too big. Because basically, if you will be throwing garbage, I don't think that you will at the same time open the garbage chute. So basically, there will be only one.
One fan.
Yep. If you open, there will be like only one garbage chute to be opened, which is 80 liters per second. So what I
Yeah.
assume is like only 80 liters per second processing this dumper and grill.
Well, how do the fans operate? When do they come on?
Continuously operate. It is continuous operating. So this
Yeah.
one is operating 80 and this 80. So what I did is just assume that when you are throwing like a garbage, you will just open one at the same time, not
Yeah.
not
Yeah.
not both. So basically, I just assume like it will be 80 liters per second.
Yeah.
Because basically, if 160, it will be two big grill, two big car dumpers and grills. So it's not cost efficient. So I don't know. Because basically, I just assume because I was throwing at the condominium. They just open only one, not
Yeah,
opening
that'd be
both the
right.
same.
Yeah. So they've got openings on each floor, though. It's a multiple
Yep.
story building, is it?
Yep. And each floor will not be opening also at the same time. They just assume
No,
one.
well, probably
Yep.
not. No.
Yep.
So
So,
you're getting the air's coming through the opening, the door opening,
mm.
and but also through this grill, is it?
Yep. So this is like above the ceiling, and this is the ceiling grill. So it will just go down and suck. But if you have open those garbage too.
Right.
So they are arguing if I need to assume like a 160,
For the return air, for the
160,
grill.
yep, or an 80.
Well, okay. So so if there's no garbage chute openings, like
Mm.
if nobody is opening a chute,
Mm.
then all the air is going through that grill, is it?
Yep.
So in that case, if you've got two fans at 80 litres a second,
Mm.
you'd need 160 through there, wouldn't you? Through the
Yep.
grill.
Yep.
So you're trying to size this grill, are you? Is that the
Yep.
question?
Yep. Trying to size the grill and fire damper because if we would be increasing it to 160, the grill size will be like it will be larger. And if it's like a 30 floors, especially if there's a 30 floors, there's too much expensive than reducing that one. So we are arguing if, because basically if I will be just throwing like a garbage, I will just open one and throw it, which is 80 liters
Yeah.
per second. And probably once done, I will just open again because I think it's just like a automatic rubber. Once you open it, throw it, and it
Yeah.
will automatically get back. So we are just arguing if do we need to allow 160 or 80 liters per second on this one.
So do you allow 80 through here or 160? And so what have you got here? Option 2, return air duct with fire damper, location to be determined by architect. Option 1, intumescent door grill in fire door. I'm just trying to understand so there's a door there. So
Yep.
you can either have a duct with a fire damper or a door
Yep.
grill in the door. And
Yep.
then this is, so people walk in here and open a chute somewhere, do they?
Yep.
Option 2 requires a return air grill in the ceiling. So who
This
are
is
you working with? You're talking to a consultant about this, are you? Or?
with Matt. This is, as the garbage room says 100 liters per second minimum or service requirement, but Matt Matthew says we need to confirm with the build others, the contractor, what fans we will be using. So we have confirmed that it is 80 liters per second for each tube. So now we are confirming what airflow we will be using. Like, do we need to assume 80 or 160? This one.
So where did the ID come from?
The idea came from them. If
The
they
contractor?
this yep, this one. If you would
Those-
look, this is their comment.
So at a glance, this is only 80 litres a second. Should we be telling the builder that this is 180 across both chutes? Thoughts on what we do here? Unsure on how this looks for Reg 126. But the code says you need 100 minimum, does it?
Yep. And the code says 100. So basically, I think we will just assume 100
Yeah,
to be compliant on the code, than to assume this like 80 or 160. They want just to need to still to comply with the code.
well, I think so, yeah. I mean, the code's pretty clear that you need 100 litres a second minimum.
Yep.
So that's your starting point. I don't know where where did the 80 come from?
This one, the selection of fan, the fan on the garbage chute.
Ah, it was selected for 80 litres a second, was it? By the consultant.
Yeah, yeah. With the other contractor, they use 80 liters per second, but the minimum for the code is 100 liters per second.
Yeah. Well, I just changed it.
So
It's not going to make that much difference.
Yep.
Just make it 100, yeah. Is that
Mm.
is that per floor or where is it exhausting out?
it's listing out on the roof. So basically, there will be one garbage chute fan on the roof.
Right.
Let me.
But
there
you've
is
got
like
have you got multiple floors that are being exhausted?
Yep, yep. So there are like 4 levels on this one. So I was thinking this will be, and there will be a like this is the fan at the roof.
Yeah.
So there are multiple levels, and the capacity of this one is 80. 80.
80 at the top, and that's to
Yep,
cover all floors.
yep. So I was thinking because they will not be opening it at the same time for each floor. We just assume like this will be 80,
Yeah.
80, 80.
So
Yep.
you're just saying, okay, so there's only one
Yep.
chute that's going to open at any one time.
Yep.
And therefore you only need 80 litres a second, but the code says 100. So,
Yep.
but you've got two fans that do 80 litres a second
Yep.
each.
Yep. So 160.
So why have you got two fans?
Yep, and those do fans, so it will be a 160.
Why
This
have you
floor
got two
with
fans? Sorry?
because there's two garbage chutes. Sorry.
Oh, two separate garbage chutes, are they?
Yeah, yeah. So I was thinking just to use 100 just to comply with the code, and we could argue that the chute will not be open at the same time for each floor. And
Well, I don't know. You don't, how do you know that? How do you know that they can't open two at the same time? You can, can't you? It's probably not likely, but it might happen. How many floors are there?
4. There will be only 4.
Yeah, okay. Oh, look, it probably doesn't matter that much anyway. It's not going to make that much difference. But so you're going to,
Or
yeah,
to be
I'd
safe, just
just work
to
on 100
comply
litres
with
a second.
just to comply with the code.
Yeah.
Yep.
Well, yeah, I mean, that's what it says. So I think that's what you need to do.
Because I've already told them this is with what we require, the 100 liters. Then they get back to me that the other contractor has only provided 80 liters and two put both fan, and they're arguing that do we need to use 160 or 80 or 100 liters? So
Right.
what I did is just get back to them that this is the code 100 liters per second.
Yeah. And what was their response to that?
Probably they'll just tell the consultant, ask the consultant what he wants, what they want, what airflow they have already provided.
So the consultant wants 80 litres a second, did you say?
No, they haven't yet provided. So they might just told us just to provide the airflow, and the consultant will just check it. So
No, I
basically, we
would
are just
say,
waiting. Yeah.
so each fan, you got two separate shafts. Each fan is 100 litres a second,
Mm.
assuming that there's only one chute open at any time.
Mm. Yeah.
Yeah.
So that's what we sent to them yesterday, that we have assumed 100 liters per second as per the AS 1668, and because that's the minimum, and we don't assume that the garbage chute will not be open at the
Yeah.
same time for each level.
Uh-huh.
So and each chute has 80 liters per second. So there will no much difference. So that's what I uh, tell them. But yeah, I was thinking it yesterday.
Yeah,
Because
100
they are
litres a
arguing.
second, whether
Yeah.
it's 80 or 100, it's not really going to affect the fan. The fan will be the same.
Mm.
And the grill would be the same, I would think. So it's not really going to change anything, but I think you need to have 100 to comply with AS 1668.
Yep. Yep. I think that's it. I'll just be waiting with the response. Consultant response.
Yeah. Okay. Oh, if you want me to have a look at it, you can send it through, but I think that seems to be what you'd need to do. Just
I
go
think
with
I'll
the
just wait for the consultant, then I'll call you again. What they have
Yeah.
provided a feedback.
Okay.
Because Troy is on leave, so I'm asking
Oh, yeah,
the
okay.
project then. Yeah. I think that's it. Peter. Then we'll talk again by Thursday next week.
Sorry?
Thursday next week we'll have a
Yeah.
training
Yeah,
again.
I'll send you some notes through for the next week's session, which is going to be on what do we got? Duct insulation. Duct insulation